Hello, students, and welcome to today's Friday Happy Math Hour. Today, I'm going to be covering solving exponential and logarithmic equations. But to start off, I'm going to review like the topics from last week, just the last topics. Okay, how to graph exponential and logarithmic equations, and then we'll start with the solving. Okay, but these are the topics that I'm going to cover today: writing logarithmic equations into exponential equations, writing exponential equations into logarithmic equations. And then comes the main part for today, for this week, which is solving exponential equations by using the same base rule, solving exponential equations with different bases, and solving logarithmic equations by using the logarithm properties. Okay, so let's begin. Again, this is a review from last week, like the last part. Okay, writing exponential equations into logarithmic equations and vice versa. Definition of a logarithm to the base a. For example, y equals to log base ax means a to the y equals x. So in other words, here on the left is a logarithm form, on the right is the exponential form. So for example one, write each logarithmic equation into an exponential equation. I believe I'm going to do one of each only because this is a review of last week. Okay, if you have log base 981 equals 2, then, right, so then we have to know what the a is, what the x is, and what the y is. Okay, we have to convert it from exponential form, from logarithmic form to exponential form. So I need to know what the a is, what the x is, and what the y is. If you notice, my a is equal to 9. My x is equal to 81. And my y is equal to 2. So then we're going to go from logarithmic to exponential. Right, so this is my answer, right? Why? Because my a is equal to 9, my y is equal to 2, and my x is 81. This is very basic, guys. Just by knowing what the ax and y is, you'll be able to go back and forth. Example number 2. Now we're going to go the other way. Write each exponential equation into a logarithmic equation. Right, so this is an exponential form. Right, so we have to know what the a, the y, and the x is, right? So we're going to get those values. And then we're going to convert it into logarithmic form. So my a, if you notice, is equal to 5. My y is going to be 3. And my x will be 125. So we're going to go from exponential to logarithmic. You see there's my y. My y is 3. My a is going to be 5. And my x will be 125. You can put it in this form, or the way the answer in back of the book is always in this form here, okay? But it doesn't matter what form it is. If you're doing the My Math Lab, the homework on the platform My Math Lab, the answer will be right either like it is here on the left or also on the right. It's the same thing. Okay. Okay, now, in order to graph without a calculator, must convert logarithmic equation into an exponential equation. Okay, that's my next thing that I'm going to cover. Examples of exponential functions, right? These are all the exponential functions. And again, this was the lesson from last week. But I always kind of review at the beginning what I did the previous week, so you guys can actually know what we talked about the previous week, and now what we're going to cover this week also. So these are all the examples of exponential functions. If you notice, it's going to be f of x equals to a to the x. The a is going to be my base, and the x will be my exponent, right? Or the variable, which is a letter, which is frequently x, but it can be y, it can be any letter or any variable. That'll be your exponent. Okay, so we're gonna be graphing. This will be when a is more than 0. Okay, so if you recall, guys, from last week, how do we graph an exponential function? The values that we always choose, or the most the x values that they want you to pick, guys, are always like from -2 all the way to 3. Okay, and let me show you why those are the values that we choose. Okay, but first, let's plug them in here. So when x is -2, right, this is what takes place. So I'm going to plug in -2 for the x, or I'm going to evaluate f of -2, right? And if you notice the properties from last week, the negative exponent becomes positive if you do the reciprocal, right? Or else the base goes to the bottom and the exponent becomes positive. So this will be 1/4. Okay, now, if I would have chosen -3, guys, -3 will be 1/8. And then when you graph it, it doesn't really, I mean, you can put -4, -3, and so forth, but the graph doesn't really change. So, I mean, that's why we always start with -2, -1, and so forth. And I'm going to show you right now when we actually graph it. When you have -1 for x, all we do is evaluate f of -1. And again, we plug in -1 for the x, which would be 1/2 to the first power, which will be 1/2. So when x is -1, y is 1/2. When it's 0, right, we evaluate it as 0. And anything, any base to a 0 power will always give you 1. So we got 0, 1. Then when we use 1 for x, we evaluate f of 1, which will be 2 to the first power, will give us 2. So when x is 1, y is 2. Then when x is 2, again, we evaluate f of 2 is going to give us 4. When x is 3, I'm sorry about that, when x is 3, we evaluate f of 3 is going to give us 8. You see, students, we don't plug in 4 because if we put in 4, it's going to give us 16, and 16 will be off the grid. That's why these are the most common values to use for x. And here's my graph. Remember I was saying that we didn't use -3 or -4 because eventually, if it was -3, right, to evaluate it, it's going to be 1/8, and 1/8 will be about right here. You see, because if it's 1/8, it means that we divide from 0 to 1 this unit into 8 equal parts. So A will be about right here, you see, so it doesn't matter. What matters is from -2 on. And if we pick in, I mean, say that we chose 4, right, for x, it's going to give us 16. 16 will be off the grid. So these are the wisest points to use for an exponential function. Okay, now let's graph a logarithmic function. Again, in order to graph without a calculator, must convert logarithmic equation into an exponential equation. So we have to convert it from logarithmic to exponential. So let's graph y equals to log a base 2x, right? So to convert it to exponential, it's going to give us 2 to the y equals x, right? So now, but instead of plugging the values for x, we're going to plug them in for y, because the work will be much easier if we plug them in for y, because y is my exponent. And if we follow the same concept as before, right? We're going to get, when y is -2, it's going to be 1/4. X is 1/4. When y is -1, it's going to give us 1/2. When y is 0, x will be 1. When y is 1, x will be 2. And when y is 2, x will be 4. And when y is 3, x will be 8. So anyway, this in red is a graph for the logarithmic function, and in blue is for the exponential, the one that I did in the previous slide. You see, so if you notice, you see here, right, when for the exponential in red, when x is 1/4, right? 1/4 means that you're going to cut this unit from 0 to 1 into 4 equal places, right? And 1/4 will be about right here, where my arrow is. So if you go straight down, it's going to be -2. When x is 1/2, it's going to give us y equals to -1. When x is, right, and then when we got 1, 0, the point there, then we got 2, 1, and then we got 4, 2, and then we got 8, 3. So this is how you graph the exponential and also the logarithmic equation. If you notice, these are inverse of each other, right? They will always be inverse of each other, because if you divide if you fold the graph at the y equals x on the origin, all these points will come over here. Okay. And again, I believe 1324 doesn't cover inverse as much as in detail as a 1314. That's why I don't even mention it. I just mention it real quick, but I don't go in detail. Now, here comes the main part of today's lesson, which is solving exponential and solving exponential functions and logarithmic functions. So to start off, to solve exponential equations without a calculator, you need to know the previous topic, such as you need to know perfect squares. All these here guys, like the 4, the 9, the 16, 25, and so forth, these are called perfect squares. Because what the square root of 4 is going to give us 2. What the square root of 9 will give us 3, and so forth. So these are perfect squares that you must know. And also these are perfect cubes. Because 2 cubed is equal to 8, right? So the cube root of 8 will give us 2, and so forth. So at least know all the way to 6. And also these are the fourth roots. These are the fourth root because the fourth root of 16 will give us 2. Why? Because 2 to the fourth power will give us 16. The fourth root of 81 is going to be 3. Why? Because 3 to the fourth power will give us 81. So at least know all the way to 5. And also you need to know the exponential expressions, right? A to the m. A is called the base, m is the exponent. And you also have to know the exponent power rule, which I explained last week also. The exponent power rule means when you have a power to a power, right? A power to a power, you multiply the powers. And finally, you need to know how to solve one variable equations, or maybe also quadratic equations, but mostly it's going to be solving a one variable equation, like something in this form, like 2x plus 8 equals to 14. You need to know all these topics in order to be able to solve exponential functions. Okay, now let's start with the first here, they call it with the first rule here. In this book, they call this rule. Let a be a positive real number with a cannot equal to 1. So here's my condition, right? If a to the u equals a to the v, then the exponents must equal to each other. Then u must equal to v. What they're trying to say here, guys, if you have the same base, right? This is a base, right? If you have the base a for both, then you apply the rule, which is you let the exponents equal to each other. Example. So you have 3 to the x equals 3 to the 5th power, correct? Are the bases the same, right? Same base, right? So we apply the rule. So when we let the exponents equal to each other, so x equals to 5. But not every time it's going to be so simple. For example, example 6. You have a to the x equals 2 to the 5th power. Now do they have the same base? No, they don't. So you cannot apply the rule yet. You have to make him the same base, right? So by knowing the cube roots, right? The cube root of 8 is equal to 2 cubed. So I'm going to convert 8 into 2 cubed because I want to make him the same base. So I'm going to replace 8 with 2 to the 3rd power, bring down the x as the exponent, equals 2 to the 5th, right? Now I'm going to apply the power rule here, or the exponent power rule, which means when you have a power raised to a power, you multiply the powers. So 3 times x will give you 3x. Now we got the same base, right? So same base, now we apply the rule. What rule? The one here above. Because when you have the same base, you let the exponents equal to each other. So 3x equals to 5. We divide both sides by 3. So x equals to 5 over 3. And again, what's good about these guys, like any other equation, that you can always check your work. So you can always check your solutions. So how does that work? Okay, I'm going to plug in the solution, which is 5 over 3, plug him into the x, right? Now this, you can put it actually in the calculator, or you can use a rule, right? Or without if possible. Okay, let me show you both, right? So this will be 32. Remember this rule here that I went over last week? The 3/5, right? A is going to be my base, which is called the radicand. I mean here, the A is my radicand. Then my n, which is the denominator, is my index. Then the m will be the exponent. So again, the base is my radicand. The denominator of the exponent is going to be my index, and the numerator is your raised to that power. So what's the cube root of 8? is going to give us 2. 2 to the 5th power is equal to 32. You can do it in this way, or else you can plug it in the calculator just the way it is here, and you're going to get 32. So that's how you can check your work. Okay, now let's do another one. Example number 7. We have 9 to the x power equals to 27. So are they the same base? Not the same base, right? So then let's see if 9 to a certain power will give me 27. So if we notice, right, if we plug in 1 for x, 9 to the first power is going to give us 9. Now let's try 2. 9 squared will give us 81, right, which is not equal to 27, which means we have to find the same base, and the same base, because 9 is not the same base as 81. Okay? So what do not the same base as 27. So what's the common base between 9 and 27? The answer will be 3. Why? Because 9 is equal to 3 squared, and 27 will be 3 cubed. You see, now we got the same base. So then we go back here to the example. I'm going to replace 3 squared for the 9, and then we'll be done the exponent, the x, and then I'm going to replace the 27 with 3 cubed. Right now here on the left, I'm going to apply the exponent power rule, which means, right, that when you have a power to a power, you multiply the power. So 2 times x will give us 2x. If you notice, now we have the same base, which is 3. So now we can apply the rule. So then it'll be 2x equals to 3. We divide both sides by 2. So x equals to 3 over 2. And again, we can always check our solution. We're going to plug in 3 over 2 for the x, for the exponent. And you put in the calculator, guys, it's going to give us 27. Or by the rule that we used earlier, remember the 2 is the index. So what's the square root of 9? It's going to be 3. Then 3 cubed will give us 27. But for now, all I do is plug into the calculator, guys, right? And we know it's a match. So I know 3 halves is a solution. Okay, now, you see, if you notice, they get a little bit more challenging after every example. This way, I'll be able to cover every possible example or every problem that's in this section here for your homework. So again, are they the same base, the 4 and the 32? No, they're not, right? So let's see if 4 to a certain power will give me 32. So 4 squared is 16, right? Does not equal 32. So let's try 4 cubed. Will give us 64. You see, it's too much. So I know that we have to find the same base between 4 and 32. So I know that 2 squared is equal to 4. And I know that 2 to the 5th power will give me 32. So I'm going to substitute 2 squared for the 4 and bring down the exponent. And I'm going to substitute 2 to the 5th power for 32. Now here on the left, I'm going to apply the exponent power rule. Right, so that means when you have a power to a power, you multiply the powers. So this is what we have, right? And now on the right, we have 2 to the 5th power. Now, do they have the same base? Yes, they do. So now we can apply the rule. So when you have the same base, the rule states that the exponents must equal to each other. Now here we're going to distribute. So 2 times x will give us 2x. 2 times -1 will give us -2. And we got equals to 5. So we're going to add 2 to both sides. So we add 2 to both sides. It's going to give us 2x equals to 7. Now we divide both sides by 2. And this is our solution, 7 over 2. Again, you can always check to make sure. So I'm going to plug in 7 over 2 for the x's. So 7 over 2 minus 1, I believe is going to give us, what, 5 over 2? So again, if you plug that into the calculator, guys, it's going to give us 32. So I know that's my solution. Okay. Let's move on. Hey students, if you have any questions as I'm going through the PowerPoint, please raise your hand up. That way the moderators can help you. They can stop me, because right now I don't see if anybody has any questions because I'm sharing my screen. So please don't hesitate to stop me as I'm going through this PowerPoint. Okay, and I'll be able to answer your questions right there and then. So let's continue. Now comes solving logarithmic equations. So to solve logarithmic and exponential equations, you need to know the previous properties, such as these here on the left are called in single log, and on the right the expanded form. So this is a product rule, the quotient rule, and the power property. Also, they work the same thing for the natural log, which is the ln, right? So let's see what we got here. Hey guys, remember, recall example number 7, where it stated 9 to the x power equals 27, right? Remember, we had to try to find the same base. Well, by using the property, the ln property, right? For the ln, you'll be able to actually to do it without finding the same base. Remember, the answer was 3/2. You can solve by using the property, by the power property of the natural logarithmic, which is the one on the left or the one on the right. I like to use this one on the right, the ln, because the ln, you're going to use it when you reach chapter 5, which is a finance chapter. Okay, that's why I like to stick with the natural log instead of the logarithmic. I like to use the natural log here on the right. So anyway, how do we solve it without having the same base? Okay, you're going to take the ln of both sides. You bring down the exponent by taking the ln of both sides, right? This is the ln. If you have ln of a coefficient here, of a variable, right? The exponent goes to the front. You see, it went from here on the left. The r is the exponent. The r went to the front. So how do we bring the x down? Is by taking the ln of both sides, right? But you have to do it both sides to the left side. You see, to the left. So now by the rule, by the property here, the power property, the exponent goes to the front. Now we divide both sides by the ln of 9. And then here we have to use a calculator, and you should get something like 3/2 or 1.5. This is what I show my students if they don't, if it's just solving for exponential, right? You can use the ln. That way they don't have to worry about finding the same base, because at times students struggle with trying to find the same base. So if you feel that I'm talking about you, right, that you're struggling, if you want, use the ln, and that will always work. Okay. Let's do another example. Okay, now before I move on, it is very important. Hey guys, the ln of a number is an actual value. You cannot separate them. For example, you cannot say divide by ln and ln. No, you have to, all this here, the ln of 9 is one value. You cannot separate them, like for example, divide by the ln or divide by 9. You have to divide by the ln of 9, because ln of 9 is a number. It's together. Okay, now here's another rule. This is a rule that we just explained, right? If you have the ln of u to the r goes to the front. Okay? And here's a rule. It says let u and r are real numbers. With u positive, then the ln of u to the r power goes to the front. Okay, here example, right? So we're going to take the ln of both sides, right? And again, not the same base, right? And here, guys, you cannot even get the same base. So like I said, even if you have the same base or not, you can always use the natural log to bring the exponent down. Right? You do it to both sides. So by rule, the x comes to the front. Then we divide by the ln of 5. And then you get to plug it into the calculator. So the answer, right? So we put approximately, because this will be an irrational number. It will never have an end. So most of the times, like in your homework, they're going to ask you to round it off to say 4 places or maybe 3 places. But I believe most of the times it's 4 places. So the answer is going to be 1.2920. How do we check our answer? Okay, I'm going to plug in 1.2920 for the x. Right? And this is what we get, right? It's going to give you something real close to 8. It can be more than 8 or below 8, right? In this case, it's below 8 because, how do we know it's almost 8? Because here, guys, we run it off here. Because again, this number is only like an approximation. That's why you will always get real close to the solution over here on the right. So 7.9996 is real close to the value of 8, which is, I know it's correct. Okay, now, let u, v, and a be positive real numbers with a cannot equal to 1. If log of base a u equals to log of base a v, then u must equal v. So in other words, if they had the same log with the same base, then the expression here, they have to equal to each other, the u and the v. Example 10, right? If there's no base, right? If there's no base, we know it's base 10. And I believe I went over that last week. When you don't have a base, it's base 10. So this is log base 10x, log base 10 of 3x minus 6. So by applying the rule, right, the single log with the same base, so by applying the rule, the x must equal to 3x minus 6. And now what we do here is solve for x. We can subtract 3x from both sides. So x minus 3x will give us negative 2x, and we just bring down the negative 6. Now we divide by negative 2. If we divide both sides by negative 2, we're going to get x equals to 3. Okay? So again, we can always check our work, the solution. So x equals 3, right? So we're going to plug in 3 for the x. So 3 times 3 will give us 9. 9 minus 6 will give us 3. So I know these are equal. So the solution 3 is a solution for this problem here. And again, it's the same rule as before. So let's do another example. Example 11. Log of x plus 3 equals to log of base 10 x minus 2 plus log base 10 x plus 3. Hey guys, in order to apply the rule, you have to have a single log on both sides of the equal sign. For example, the ones on the right, is not a single log. So that should be your first step. Again, to apply the rule, the single log must be on both sides. Use a product property on the right side. So recall, guys, from the property from before, from last week, if this is called expanded form. So to put it into a single log, right, if it's plus, it's going to be the product. You multiply them. Now they're both, right, the same log and the same base. Log of base 10, log of base 10 on both sides. So then we let the u, right, we let the x plus 3 equals to the x minus 2 times x plus 3. Apply the rule. Now here we get to FOIL, right, or multiply the binomials. So again, we get x squared plus 3x minus 2x minus 6. Why? Because x times x will give us x squared. X times positive 3 will give us positive 3x. Negative 2 times x will give us negative 2x. And negative 2 times 3 will give us negative 6. Now the 2 in the middle, right? These two terms can be combined. So it's going to give us 3x minus 2x will give us this x. Now since we have a quadratic here, we have to let it equal to 0. Let everything equal to 0. Set the equation equal to 0 on the left side. So I'm going to send the x and the 3 to the right side by doing the opposite. If it's plus here, if it's positive, I'm going to subtract also with the 3. So it's going to be minus x minus 3 to both sides. That way on the right, it'll be 0. On the left. So we have x squared. The x's cancel. So we have x squared minus 9. Now we get to factor. So again, this the factoring PowerPoint, I believe I did it in week 3. So you guys can recall, right, x squared minus 9 is going to be x minus 3 and x plus 3. So then we said both binomials equal to 0. So we have x minus 3 equals 0 or x plus 3 equals 0. So here on the left, we're going to solve for x. So x equals to 3. And on the right, x equals to negative 3. So these are my two solutions. Okay, now, before I continue, guys, if you guys have a calculator there with you, plug in, just put log of a negative number, log of negative 3. If the logs cannot be negative, nor the natural logs. So for example, if you have log of negative 3, it's going to say error, which means it's undefined. There's no solution. Also, if you plug in 0, it's going to say error also, because the logs have to be more than 0. In other words, it cannot be 0. They have to be more than 0. But let's pretend that you guys didn't know that, okay? So here, let's check our work. Our solutions. So we're going to check both x equals 3 and x equals negative 3. So let's check first the x equals negative 3. So I'm going to plug in negative 3 for every x, right? So here we're going to have not defined, right? Because negative 3 plus 3 will give us 0. You cannot find the log of 0. And here we're going to get negative 5, and here we're going to get 0. Yeah, so the negative 3 is not defined. Because if you plug into the calculator, guys, it's going to give you error or not defined. So in other words, the value cannot be negative 3. Not a solution. So now let's plug in the 3. Okay, the value of 3. So we put in 3, right? So it'll be 3 plus 3, and here will be 3 minus 2, and here will be 3 plus 3. So we get log of 6, log of base 10, 6. This is 1, and this is plus log of base 10 of 6. So let's simplify. Right? Log of 1 is going to give us 0. And you put that in the calculator, right? Because it's base 10, you can actually put it there. So this will give us log of 6 equals to log of 6, so I know this is correct. So that's my solution. Let me go back. My solution will be x equals to 3. Okay. Now, again, let's solve the same thing, guys. But now, example number 12. We have log of x, log of base 10x equals to log of x plus 3 minus log of x minus 1. And again, since we don't have no base, we know it's base 10. Okay. So we have to have a single log on both sides to apply the rule. So here, guys, we're going to use a quotient. For the quotient rule, right, if it's subtraction, it's going to be division on a single log. So now, since we have both same base in the log on both sides, so we apply the rule. So the u must equal to v, so the x must equal to x plus 3 over x minus 1. Now here, guys, I'm going to cross multiply, I believe. Right, so x, so the x on the left side is the same thing as x over 1. If you cross multiply, it's going to be x times x minus 1 equals to x plus 3 times 1. Or you can say here, you can multiply both sides by x minus 1. That way, the x minus 1 will cancel here on the right side. Or you can cross multiply, whatever you want. So this is what we should get. If we multiply both sides by x plus x minus 1 on both sides, we should get this. Or if you cross multiply, this is my result. Now here, I'm going to distribute the x. So it'll be x squared minus x equals to x plus 3. Now, since we have a square, right, a quadratic, we're going to let it equal to 0 by sending the x and the 3 to the left side, right? So we have here, we have x squared, negative x minus x will give us negative 2x minus 3. Now we have to factor, okay? And again, to factor, right, is going to be x minus 3 and x plus 1. And again, I went over this PowerPoint on week 3. If you guys don't know how to factor, please get help in the tutoring department, or else come see me during my Sunday numbers, or you can actually come during my office hours and I'll be able to help you. If you need my contact information, just send me an email and I can provide you with my contact information. That way I can tell you more about my office hours and also Sunday numbers. Okay. But anyway, these are the factors. These binomials will be the factor of x squared minus 2x minus 3. So then we let m equal to 0. So we get x minus 3 equals 0 and x plus 1 equals 0. So we're going to get 3 and negative 1. Okay. Now again, let's repeat. Let's check our solution, which will be here on the next slide. So remember, guys, right? It cannot be negative 1 because if we plug in negative 1 there, it's going to be undefined, right? We cannot do that. And again, because if you put this in the calculator, guys, it's going to be error, not defined. So negative 1 is not a solution. Now let's test the 3. We're going to plug in 3 for every x. Okay. So on the left side, we have log of 3. On the right side, this will be 3 plus 3, and this will be minus. So we're going to get log of 6 minus log of 2. Now here, you guys, you can use the calculator if you want, right? Because you can, because these are base 10. Now, but say that you want to do it by hand, without a calculator. And if you remember, guys, this one here on the right, the log of 6 minus log of 2, right? If it's minus, right, we're trying to put it on as a single log. So it's going to be the quotient rule or division. So log of 6 minus log of 2 is equivalent to log of 6 divided by 2. And 6 divided by 2 is going to give us 3. You see, so these are the same thing. They're equal. They're equal. So 3 is a solution. Now here comes another rule. If a and u are positive real numbers with a cannot equal to 1, then a raised to the log of a u equals to u. So in other words, if you have, right, this is called my base here, the base. And on the exponent, right, if you have log of the same base, then the u, right, that's why this is what equals to, it equals to the u. Okay, whatever values here, this will be, this on the left side will simplify to. Let's do an example, guys. How do we solve something like example number 13? Here's how. Need to cancel the log of 3, right? So my base is 3, right? So I'm going to put a big 3 here, guys, right? So I'm going to use a big 3. And again, here's the explanation. Let the expressions on both sides of the equal sign be the exponents, and the base of the logarithm be your base. So in other words, these are going to be my exponent, these right here. But since this is the base 3, right? So I'm going to put like a big 3. This becomes your exponent. And what you do on the left, you also do on the right. Now by this rule here, guys, right? By the rule, this is equal to 1. So we just bring down the 6x minus 2 equals to 3 squared. Now 3 squared is equal to 9. Now all we do is solve for x. We add 2 to both sides. So it's going to be 6x equals to 11. Then we divide by 6. So that's my solution. Now again, we can always check our work, right? So let's check it. Right, so this is example number 13. So the answer was 11 over 6. So I'm going to plug it in for the x. If you plug in 11 over 6 for the x's, right here, the 6's are going to cancel. So we're going to have log of 3 equals to 11 minus 2. Now 11 minus 2 is equal to 9. Right, now log of base 3 of 9 is equal to 2. And here, guys, you can apply the change of base, because this, you cannot plug in the calculator just the way it is, because this is not base 10, it's base 3. Or you can use again, you can use the change of base, which I believe I explained last week. Or here, guys, you can convert the 9 into 3 squared, right? Because 9 is equal to 3 squared, then by the rule, the 2 goes to the front. And log of 3 is equal to 1. So in other words, you can apply the change of base here, and you're going to get 2. Or you can do it by converting the 9 into 3 squared. Then the 2 goes to the front, and log of base 3 of 3 is equal to 1. So 2 times 1 will be 2. Hey guys, I believe that's the end of the PowerPoint. I think I'd finished like early. Um, let's see if you guys have any questions, and if not, well then I guess we'll just wrap it up. Okay, let me go back to see if anybody has any questions. Let me stop sharing my screen. Do you guys have any questions? Anybody?
No, thank you, Mr. Dasasi. I mean, that was a refresher for me.
All
Okay.
right. Well, thank you, Mr. Isasi. That's it. And let me just make an announcement.
Okay. Okay.
Yes, so next week we will have for 1314 finding zeros of polynomial functions, and for 1324 simple and compound interest annuities. Thank you so much again, Mr. Isasi, for presenting today, and thank you for everyone coming and being a wonderful audience. We hope to see you again soon. And don't forget to do the quick survey that we posted last. Thank you.
Bye bye, guys. Thank you very much.
Bye-bye,
Thank you.
Mr. Dasasi. Thank you.